Good afternoon, everyone. My name is Kevin Dressler. I'm the Operations and User Facility Director here at the 2DCC. Today we're going to have a talk by Dr. Nassim Alem, who's going to be talking on some TEM studies and some other studies related to characterization of 2D materials. First, Dr. Alem comes from Northwestern University with her PhD, and then most recently she did her postdoc at University of California, Berkeley, and also the National Center for Electronic Materials at Lawrence Berkeley National Lab.
Electron microscopy.
Oh, electron microscopy, sorry about that. So anyway, without further ado, Dr. Lem will be giving her presentation, but I want to let you know that this webinar is being recorded, so you can always view it later, so voice and also the slides will be flipping through. Thank you so much, and Dr. Lem.
Okay, thanks for the introduction. So today I'm going to be talking to you about some of the applications of electron microscopy and how we can use this technique to understand materials and their structure, defects, grain boundaries, and basically what type of microstructure we can have. In particular, it's a 2DCC seminar, so the talk's focus will be on 2D crystals and in particular TMD, transition metal dicarbonates. Okay, I'm just going to be using. So before I go ahead and get started with my talk, I'd like to tell you a little bit about the objective. Why do we care about understanding the defects and understanding basically the microstructure? It all comes down to understanding how to nano-engineer nanostructures to get certain properties that we are interested in. For example, in 2D crystals, these materials can have interesting properties in catalysis. We know TMDs they are very good catalysts for hydrodesulfurization or, for example, hydrogen evolution reaction. They are, right now, there's a lot going on to understand how these materials can be incorporated into electronic and optoelectronic devices, or photovoltaics, cells, energy applications, and all that. But if we look at these materials, we see that the atomic and chemical structure of the defect and their stability and dynamics, the grain boundaries, interfaces, these are the microstructural features that are going to dominate and they're going to govern the macroscale properties that we are going to get. And by defects, what I mean is not necessarily just a single vacancy or defect. It can be anything that stops the periodicity of the lattice. For example, interfaces, dopants. They are not classically as we known as defects, but anything that can interrupt the periodicity of the lattice, we can consider them as features that can introduce some interesting properties. We know already so much about how these microstructural features can introduce properties at the collective level, at the macro scale. We know so much already. But what we don't know is when we go at the atomic scale, at very small size scale, what we don't know is their atomic structure, their chemistry, and also their stability and transition dynamics. And that's very important because if you understand how these materials, their structure of these materials and their local properties at the small size scale, then we can engineer them, we can basically manipulate them and understand how these can directly link to what we want at the macro scale. And for that, I'm proposing electron microscopy as one of the best tools you can use to probe such as atomic structure, chemistry, and even local properties. And my talk today is going to be mostly on that. So this slide, I like to start with this slide because this is not a TM, necessarily TM talk. We are talking about 2D crystals. Some of you know what you can do with the TM. Some of you have heard about aberration-corrected TM, but some of you may not be familiar. And this is an image of graphene. Right there in the middle where I have written graphene, there is a layer of graphene. And this is what we know of graphene. It's basically carbon atoms forming a honeycomb structure. And we don't really see anything here. And that's because we are using a conventional TM where there is no aberrations corrected in the lenses. And when with a microscope like that, we do not have the necessary resolution to resolve the lattice. And that's going to be very hard for us to look at the defects in these materials because we basically simply do not have the necessary resolution. However, when we correct for the aberrations, we are going to improve the resolution quite significantly. And this is just an example. This is not a microstructure. This is actually a galaxy, a picture of a galaxy that's taken by Hubble. You can see that this image on your left is an image that is before the aberrations in the lenses are corrected, and this is after the correction. And you can see a lot more finer structure in this sample, in this image, all the details and all the features that basically we wouldn't be able to see without the correction. We can do the same thing, microscopists can do the same exact correction in an electron microscope in the lenses. And by doing that, we can improve the resolution quite significantly to a point that we can actually resolve the atoms. We can resolve, okay, let me just adjust this a little better. We can resolve the atomic structure in graphene. This image that I'm pointing to, this is actually a single monolayer of graphene. You can see the atoms are white here. The centers of the hexagon, in the middle of the hexagon in graphene, there's nothing, is a darker color, dark gray. This image is taken by our microscope at Penn State, the Titan cube. Here, although this is an image from our microscope, but I'm not showing this image on the left side is actually an image that we took from the microscope from the National Center for Electron Microscopy at Berkeley Lab, because our room is really small and we really cannot get a very nice image of our microscope. It's it's pretty. It doesn't really show how big it is. So I always use this image. And our microscope is basically pretty much, I would say, almost identical to what we have at NSEM at the Berkeley Lab. So this microscope, for people online and for you, if you are interested to know something about it, we have aberration correctors incorporated in the column for both high-resolution electron microscopy work and also scanning transmission electron microscopy. So in two different modes, we have aberration correction capabilities. We also have a monochromator, GAN monochromator, that improves the energy resolution of the GAN down to as good as 100 millieV. So it's pretty good if you want to do spectroscopy. And we can basically easily get sub-angstrom resolution. So 0.5, 0.6 angstroms is achievable. And also we can use it for different voltages, for beam-sensitive materials, or for materials that require higher voltage, higher beam energy. So this is basically just an introduction to the microscope that I'm going to most of the data is coming from here. And and the talk is going to be focused on transition metal dichalcogenoids in particular. So we know, basically, I think this is a 2D CC, so everybody knows 2D, everybody knows transition metal dichalcogenoids, but this is basically the structure. I don't want to spend time on it. This is the top view, and the cross-sectional, you can see basically we have the transition metal that's sandwiched between two chalcogen layers on the top and on the bottom. In this particular talk, I'm going to be talking to you about how we can basically, what is the microstructural features in these materials, for example, from defects, what type of defects do we have, what kind of atomic structure, chemistry, and then moving towards how we can further tune the properties of these 2D TMD through crystal defects. And again, the definition of the defects I'm talking about is not the traditionally what we know as defects. My talk has 3 different subsections. In the first one, I'm only talking about just in particular the defects we have observed in some of these TMDs, like dislocations or their stability and dynamics. Then we move forward into how we can stack these 2D crystals, and what is the role of the defect in nucleation and growth of these stacked layers, and what kind of properties can emerge from that. And in the third one, in the third section, I'm going to be talking about alloy TMDs. In other words, what happens if I go ahead and substitute one atom with the other? What kind of structure am I going to get? What kind of properties could emerge from such structures? Most of the stuff I'm showing you in talk is going to be from scanning transmission electron microscopy imaging. So I'm going to have this little demo for people who just wonder, okay, how am I going to, what is this technique? What am I going to use? How am I going to use it? Just in our microscope, things are upside down. So, the source is on the top, detectors are on the bottom. This image, actually, I got it from my colleague and good friend, Dr. Ramas, in SuperStem. And their microscope is actually inverted, so the source is in the bottom. So the way it works is you have a source, and then you use some lenses, you form a probe, and then you scan your probe on the sample, and then the beam is going to transmit through your sample. That's what happens in the TM. And then it falls onto a detector. And then you use that transmitted beam to go to, basically you use that to do electron energy loss spectroscopy. Basically goes to the spectrometer for you to understand bonding, chemistry, so on and so forth. Then you have the other part of your beam that diffracts to much larger angles. And you are going to, we're going to use that to have the diffracted beam fall onto an annular dark field detector that is in blue color. You can see that here. This is my what we call annular dark field, ADF, and we use that to form an image. Okay, so in this case, this image that you see is an ADF image, ADF stem image, annular dark field image. So the interesting thing about these images are wherever you see an intensity, that means there is an atom. And the heavier the atoms, the higher the atomic number, the brighter that atom. So it basically is directly related to the intensity is directly related to the atomic number. So by looking at this is basically what you are looking at is a single layer of tungsten disulfide. You can see very tiny bright white dots. These are tungsten atoms. And you can see that we have one grain here, another grain there, and there is a grain boundary right there, right in the middle. If you look at this sample, the first thing that came to our eyes was, tungsten atoms are big, so when they are missing from the lattice, you immediately notice them. This right there, you can see a missing tungsten atom, but tungsten is very big, and it's very unlikely, like you don't see that many vacancies in these samples for tungsten because they are not beam sensitive, they are not ejected by the beam. Yes, occasionally we might see them, but as we started looking more and more into this sample, we observed that sulfur knock-on damage threshold is right around the energy we use, 80 kV, for the imaging the samples, and basically they get ejected from the lattice, they come out, move around on the surface, and so as a result, these samples generally are sulfur deficient, and we have a lot of mobility of these sulfur atoms on the surface. And so if we go back, so here is what we showed. So you can see just to reiterate again, these bright dots are sulfur, tungsten, and right in the middle of these triangles, you see a beam intensity. These are the sulfur columns. So now, talking about this grain boundary, because grain boundaries are one form of defect, and if you look at them, we see right there, you can see the half plane that basically forms a dislocation for me. Classically, when we talk about dislocations, we refer to them. And going back and just putting tungsten and sulfur atoms on these images, in this case, tungsten is blue and sulfur is yellow, we can see that we have a 6-8 defect right at the core of this dislocation. So this is another grain boundary right there that you can see. This is a low angle grain boundary. So you can see the red dashed and the blue dashed lines. They form a 12-degree angle, misorientation angle. And if we zoom in one of these, and these are dislocation cores that you see, again, these are half planes. You can see these half planes. And right there, we can see, again, in one of these dislocations, we can easily see the 6-8 cores. And going to, we collaborated with the simulations, by the way, I'm showing for the tungsten disulfide work is done by Dr. Jakobson in Rice University, our collaborator, and the samples came from Dr. Terone's group in Penn State. So I forgot to mention that at the beginning of the talk. So you can see that this through simulations, we wanted to know what type of stable low-angle grain boundaries we have, and we observed that basically as you have the 6 dislocations packed by a certain periodicity, about 1 nanometers on a line, you can form these low-angle grain boundaries, and that's how they simulations predict. And in fact, they also can introduce empty states in the band gap. So here, this is the band structure of tungsten disulfide. Black line shows the band structure without any defects, and the blue line shows the band structure where we have these 6 dislocations incorporated. So you can see that locally the electronic structure is basically modulated due to the incorporation of these defects. So this is another area of the grain boundary, another area of the sample with a grain boundary. And by looking at the two sides, we notice that on one side we have only sulfur tungsten atoms showing up, the blue dots. But on the other side, we had both tungsten and sulfur. So sulfur had a significantly bigger, like larger intensity that we couldn't see on the other side. So the first thing was maybe there is some sort of phase transition happening in these samples. But by tilting the sample a little bit more and exploring, we observed that sulfur actually comes in, the intensity of sulfur shows up, and as we tilt, it disappears. And by further looking inside in this sample, we found out that basically right at the grain boundaries, these samples are buccal. And there is quite a lot of strain associated with the grain boundaries. So if you look, you can even see some of these atomic layers you can see the distortion. And for these grain boundaries, as we did the calculation to compare to our experimental data, we observed that for these grain boundaries to remain stable and basically maintain their structure, there has to be buckling of the grain boundary right at the boundary for them to basically remain like the way we see them. And so this points actually to the fact that we have quite a lot of strain. And we were interested to observe this strain. So we went ahead. This is a low angle grain boundary, and we were interested to look at the intensity, the strain at the grain boundary. So we went ahead and turn off the lights. I'm not sure how clear can be seen from there. So what we observed was right at the dislocation cores, right, if I go back, for example, you see these are my dislocation cores, right, in black areas where I have this half plane. This is my strain map, shear map. You can see that I have the blue color or the green color is the compression, and the red is tension, expansion. So you can see that right at the dislocation core, I have tension, compression and expansion of the bond, and that basically shows that there is significantly quite a lot of local strain right at these dislocation cores. And so that basically confirms what we have observed regarding the buckling of the grain boundary. We also looked at the strain in the YY and XX direction, and we observed the same thing, that at the dislocation cores, we actually do have significant amount of strain. Also, by just looking at the form of the shape of the 6A dislocations here, we can see that there should be a mirror symmetry at least along this direction in my 6A dislocation, but I'm losing that. There is no mirror symmetry, and the defect is actually distorted. And this is due to the shear. And here in the simulations, our colleague, Dr. Jakobsson's group, they applied 0.02 radians of shear into this model, and we observed the same sort of a distortion that we observed in the experimental data. So we were able to see that there is quite a lot of shear here. We were interested to understand how these grain boundaries move, how these dislocations move and migrate. And this is a movie that I'm going to be starting soon, but before I start, I want to point to where the dislocations are. You can see them here, here. And as I start the movie, you can see that these areas actually, the dislocation glide up and down. Hope that is right there. So you can see that in this area, I don't want to put the laser pointer, but this area you can see dislocation motion and grain boundary migration. So if you look at the individual frames of this movie, we see that in this case, we have numbered the rows, the dislocation from 4, number 4, row 4. It moves to number 5. Then later on, from 5, it's going to move to 6. And when we look at this, these are individual glide movements, individual movement through glide. And by looking at the energetics of this motion, we observe that, so regardless whether we have one sulfur in the dislocation core or two sulfur atoms, because sulfur is very mobile, it can move up and in and out. We observe that the energetics of the motion are pretty low. And that's because, the sulfur basically can form new bonds. It's going to break the old bonds and then can have the dislocation, the 6A dislocation move pretty with relatively low energy, which in this case, for the case of one sulfur, we have about 1.4, pretty easy to be provided by the beam. In this case, you can see another movie where this is a pretty large angle grain boundary. You can see that 1, 2, and then the grain boundary is already very sophisticated with complex dislocations. I'm going to play the movie. So you can see that the movement of the dislocations are coupled together, and it's pretty complex. So here you can see 4 different frames from this movie with the same frames, but the dislocations laid out on top. And you can see, as I said, as you watch in the movie, you have higher density of dislocations, more complicated structures, and their movements are coupled together. So why do we care about this? Because we observe the structure of the defects, their migration dynamics, and that's very important if we want to design devices or understand, what kind of grain boundaries we might be interested in, what kind of electronic structure can arise from them. So that can basically connect us to the macro scale properties. In the second part of my talk, I want to talk about heterostructure. So now that we know a little bit about the defect structure, how can we stack up 2D crystals? What is the role of the substrate defects on the nucleation of the second layer, and what kind of properties can emerge from that? For that, we went ahead and made a freestanding heterostructure directly on the TM grid. The idea was to minimize sample handling and basically sample damage, and to make an intact heterostructure that right after the synthesis, we can directly put them into TM and study them. For that, we went ahead and transferred a layer of graphene. We started from graphene because that was the material that still was the simplest 2D structure that we knew and we were most comfortable with. We transferred the layer of graphene onto the TM grid, and we went ahead and put the sample into molecular organic CVD in Dr. Redling's group, and grew some tungsten diselenide that was basically done in by Dr. Robinson group. So here is my graphene film without any growth. It's just a freestanding graphene that you can see in the microscope. And then after growth, you can see these triangles that we grew tungsten diselenide. By looking at this image, you can see that you have these triangles that are pointing in 2 opposing directions, which basically 60 degrees angle, which indicates that there is a certain crystallographic orientation relationship between my tungsten diselenide and my graphene, and basically I have epitaxial growth. These shows are diffraction studies that in fact shows how graphene and tungsten diselenide are oriented with respect to each other. And we looked at quite a lot of different triangles, and we saw that mostly we have this epitaxy, except for some few cases where there is a small misorientation angle existing between the 2 layers. And now knowing the diffraction pattern and the spacing, we went ahead and basically created a structure on how tungsten atoms are going to be lined up with the carbon atom underneath, and this is basically what we observe. So that's what we have seen, and these green and orange triangles basically point to the triangles that we observe in our experimental data as the two opposing directions that basically exist in the epitaxial growth. So these triangles mostly are single layer. Some multi-layer areas are observed, and they are mostly zigzag metal terminated. They're structured at the edge. And so we were interested to know what is the role of the defects on the of the substrate for the growth of the second layer. And in this image, I'm showing you an area where this line is basically showing a graphene grain boundary. You can see on the two sides, I have epitaxy, and I have a single graphene. The red hexagon is showing graphene. On the other side, it's the same way. But if I look at the way tungsten diselenide and graphene are oriented with respect to each other, we see that there is a certain 16-degree angle between these two grains. And in this case, you can see that tungsten diselenide diffraction pattern is basically a ring, meaning right at this line, because of the defects on graphene, I am having a lot more nucleation along the grain boundary, and basically these defects are promoting nucleation of the second layer. So we were also interested to see, okay, this technique that we have, can we grow other types of heterostructures through other types of synthesis techniques? And we went ahead and used powder vaporization technique, and we decided to grow moly disulfide. Instead of tungsten diselenide, we grew moly disulfide. We observed the same thing. This is a stem image, so annular dark field stem. So you can see the triangles as white. And the interesting thing is you can see the triangles, there is no epitaxy, they point to different directions, and our diffraction pattern shows the same thing. So no epitaxy is observed, and this could be due to the fact that here our temperature for growth is a bit lower, number one, and also number two, it's a different growth technique, so it has different conditions as a result, and in this case we didn't get any epitaxial growth. In terms of their optoelectronic properties, we were interested to know how the optoelectronic properties differ for the case where we have a freestanding graphene versus where we have a substrate. In this case, I'm showing the epitaxial graphene. And you can see that there is a significant quenching of the photoluminescence response when my tungsten diselenide is on graphene, freestanding graphene, which is due to the fact that we have efficient transport of charge carriers in the suspended case, while in the EG we do not observe such a behavior. So that basically can show how just the interface structure and the surface can dominate, can basically govern my macro scale properties. The last part of my talk the last part of my talk is going to be on alloying in 2D crystals. For this part of the work, the samples are provided by Dr. Terrones' group, and the simulations we closely work with Dr. Crespi group at Penn State, and they provided a lot of feedback. And for the imaging, like the previous part, we used our Titan cube at Penn State. So the idea was, okay, to see, okay, can we mix these, can we create an alloy structure, and what kind of structure, what kind of chemical structure can arise from that, and what kind of macro scale properties could, arise from, such an alloy. Also, we were interested to know, by mixing these alloys, what kind of doping we are going to get, what kind of structure around the doping. Do we have displacement of the atoms and strain showing up as a result of the alloy? We went ahead and got some samples of tungsten moly disulfide from Dr. Terrones' group. I'm not sure how clear that is, but these are the triangles sitting on a silicon wafer, and we went ahead and transferred them onto a TM grid. So here, I'd like to show you first the work that first we worked with Dr. Terrones to understand a little bit about the optical properties of these flakes. As you go along this arrow from the left to the right, we were able to look at the photoluminescence response and the Raman, and we observed that there is changes in the PL position and also the intensity of the Raman for tungsten disulfide and moly disulfide as a function of position. We saw that the peak is shifting, which basically told us there is some suggesting that laterally as we walk from this side to the other, there is some changes laterally in the chemical composition of these triangles, and also we had some indication from some other Raman work that there might be even strain in these films. So we went ahead and looked at the films using transmission electron microscopy. This is my triangle, as you can see. This is a tungsten moly disulfide alloy. So we went ahead and started imaging this triangle from the edge. You see this blue triangle right there. And you can see here is an image of a single layer tungsten disulfide. You can see that so in the bottom image, I am showing the position of the tungsten atoms only. The black dots are the position of the tungsten atoms. And there are two areas here where you do not see, you see a missing tungsten. And in fact, it points to here and to here where I have an atom, but it's dimer. And that is moly. That's molybdenum atom that has replaced tungsten. So it wasn't picked up in this image because moly has lower atomic number, almost half of tungsten, so it has lower intensity. So it just cuts off, the intensity cuts off before we even reach that level, and we do not pick up the moly. That was the whole purpose of this image. So we go ahead and I'm showing you here as we go to higher magnification in one of these areas. Right there, this is my moly atom, and if you look at the intensity, the atomic intensity, you see that tungsten and 2s, and then with moly we have a much lower intensity, which basically confirms that here we have a molybdenum atom. So now as we go further inside the triangle, right here we see that the number of moly atoms are increasing. You can see these dots, these small triangular features. And in my lower image, I also see a lot of missing tungsten atoms here. The composition of moly atoms calculated from these images are increasing from 0.13% to 2%. And then as we go further, almost to the center of the triangle, we observe almost 50-50 mixture of tungsten and moly. So they are pretty much mixed. And if you look at this structure, you see that number one, I have formation of chains. There is a certain, this is not a random alloy. We have moly and tungsten forming chains in a certain direction. And that was something that was very interesting for us to observe, and we wanted to know more about it, and also understand the length of the chains and all that. So we went ahead and yeah, you can see that. So we went ahead and there is an image here that I'm not showing. Yeah. Okay. So basically, I am showing. I don't know what is going on. So I'm showing this image. For some reason, it's showing on my laptop, but it's not showing there. So, but we went right there, and along these three edges 1, 2, 3, we went ahead and looked at areas that are very close to the center of the triangle, parallel to this edge, parallel to this edge, and then parallel to this edge. We wanted to know if this chain formation has any correlation with the growth edge. And that's the image that is magically missing from my presentation. So in one of the edges, we saw that the edge one is basically this edge, the top edge in the triangle, the horizontal edge in the triangle, and we saw chains that are horizontal. Then we went ahead and looked at the edge that is in this direction. So imagine if my triangle is somehow like this. There is edge like this that at the center I see the chain parallel to that edge. And then in the third one, I have an edge, this edge of the triangle, again, if you think of a triangle like that, this edge of a triangle, along that edge, we saw that at the center, we have this chain formation that is parallel to that particular edge. So we saw that this chain formation has some correlation to the growth edge. Okay, this image is missing. I don't know what's going on. The same image now. We went ahead for edge one, that was for one of the edges. That we went ahead and looked at the. We wanted to make sure that quantitatively this chain formation is actually real. It's not a illusion, to the eye. So we went ahead and looked at the length of the chains in 3 different directions for that particular image, vertical and the horizontal and the 2 diagonal regions. And we observed that in the horizontal manner, the chains are longer by 22%. Then we went ahead to the diagonal edge, and we observed that the one that looks like, this is the longer, the chains are longer in this case. We also, measurements, like calculations, showed that this edge is also longer by 19%. And for the other case where you have these edges, in this case, again, like diagonally longer in this direction, at least by eye, we observed that measurements also showed that this edge is longer by 9%. So that was very interesting because, first of all, we see that there is formation of chains quantitatively. It is shown. It's, by the way, these calculations we did with Dr. Crespi's group. Also, we went ahead and tried to understand what can be understood from these alloys. Imagine tungsten and moly, they have very similar electronic properties, but they have very different masses. That can mean that they can have very different phonon vibrations. And that can have very interesting and can lead to phonon anomaly, and that can basically create an alloy for me that is vibrationally anisotropic along or perpendicular to the stripe. So if I go along the stripes, and basically they did calculate the phonon frequency, and they basically showed that observed the splitting of the the phonons at the in the K space, and the fact that MO, S2 and W2, they have 2 different phonon frequencies. So along the chains and perpendicular to the chains, I have 2 different phonon vibrations, and therefore 2 different thermal conductivities. And that can be very interesting because it can have applications in the case of anything in terms of, like, for thermal conductivity applications. It can be an interesting concept to consider. Okay. Well, I am at the band gap change in tungsten moly disulfide, which is not showing anything. I can also have my own laptop. Okay. So continuing to understand the electronic properties of these alloys, we went ahead and did an electron energy loss spectroscopy to understand whether there is a band variation in the band gap in this material. We were not expecting much of a change, but to make sure, basically to confirm our understanding, we went ahead and did electron energy loss spectroscopy at the low loss region. Um, to understand, to see the rise of the band gap in these three different locations, the blue, the green, and the red. And we observed that, yes, there is a small modulation in the band gap across the single domain crystal, which was expected from 1.75 you can see to 1.96. Again, calculations from Dr. Crespi confirmed the same thing. We did calculate basically the field spectra at the low loss region, which indicates the same basically rise, the same variation, and we also observed the small movement of the interband transition right at this area, at the about the 3 eV, which you can see here comparing to the calculations. So basically, we observed that these alloys can be vibrationally anisotropic but electronically isotropic, which can be very interesting for thermoelectric applications. So just to wrap this up, just by looking at the structure of an alloy and combining with simulations, you can see that we can understand a lot about the structure and the emergent properties that these materials can have. So, this is a very powerful tool, especially when it is combined with DFT. The other question we were trying to answer was whether when we mix alloy and tungsten and moly, whether there's going to be any displacements introduced around the dopant sites, around the substitutional atoms. And for that, we went ahead and we imaged, as you saw, we had already imaged the material right there, right in this middle of this image. You can see this is a molybdenum atom that has replaced tungsten. We went ahead, I don't know why it's not showing. Oh, this, okay. This is, the map is not showing, but this is actually a map that shows these bands, these lines that you see. These are the bond distances between my between my transition metal atoms in terms of the picometer. And what we observed, I really apologize. We tested the computer before the talk and things were okay. We observed that the bond distances are not changing around the moly atom. So there is you can see from just this top little area that is showing that about maximum like plus minus 10 picometer bond length changes, which is normal given that this within the error of experiment and the error of measurement. 10 picometers is pretty within the error. And simulations again by Dr. Crespi showed the same thing, that when we replace moly in place of tungsten, we are not expecting any changes around moly in terms of shouldn't be any displacement. But as we started looking at this sample around the moly dopants, we observed that sometimes moly likes to couple with sulfur vacancy. So a lot of times we saw that these moly atoms are coupled with sulfur vacancy. This is an example here. In this box, you can see two lines, green and blue. They show the sulfur variation, the intensity for sulfur right here in the bottom, that we do not see a variation. But in this case, for the blue triangle, for the blue square, you can see these two lines, the blue and the brown. And right there, you can see a missing sulfur atom right there, which is right next to the moly atom. So calculations again by Dr. Crespi showed that there is an affinity for the sulfur vacancy and moly to couple together when the system is charged, and we are looking at the sample in the electron microscope, so it's not surprising for us. This is all the calculations. Sorry. All the calculations, all the they did. And so basically what we observed is, okay, we can actually, the interesting point is we can use moly to collect vacancies in this TM-lithium. So let's say you can have a dead zone area where you introduce moly deliberately just to collect sulfur vacancies. That can be a smart way for us to control the vacancy density in the samples. Um, Going back to these structures, what we observed was, again, here you can see this area where I have one sulfur vacancy. The intensity of my line here, my spectra is showing that. And then we went ahead and this is right next to Mali, by the way. So here is my Mali atom. And when we went ahead and looked at the bond length around the Mali atom, we observed that when Mali couples with the sulfur vacancy, there is going to be bond displacements happening. So on one side, this is a picometer. The scale bar shows the values are in picometer. You see on one side that the bonds are red, the other side the bonds are blue. The map that did not show properly was something like this region, something like this region. We had yellow, green, blue areas that all show that, the variation in the bond length is about 10 or so picometers around the region. So these black dots here are Mali atoms too, but they happen to not have any sulfur vacancies around them, and you don't see any bond length changes. However, in this one, we have sulfur vacancy combined with the Mali. And you see that the bonds are, they shrink on one side, they expand on the other side. We wanted to understand what's happening. Again, this map is not showing. It's very strange. And we observed that, so you can imagine, I really apologize, but this map that we see here that has red expanded lines on one side and blue shorter lines on the other is exactly what I was going to show here. That unfortunately is not shown properly. And so here, if we compare that map with this, what I'm showing, the calculations from Dr. Crespi, we observe that let's say when we have a Mali atom next to a sulfur vacancy and a lone sulfur atom, we will have a displacement map similar to this. However, if we allow this structure to relax, what happens is that the sulfur atom is going to move down from here. It's going to move down and place itself in the plane of the transition metal. And as it comes down to this plane, to the tungsten Mali plane, there is going to be distortions in the bond. So by changing the sulfur position along the z direction, we are going to have a different map, which again the map is not showing. The displacement map is going to be similar to what we have observed here. So we have very red lines on one side and blue lines on the other. And for this displacement to happen, we also have calculated the energy associated with the sulfur position, and we observed that when the sulfur comes to the middle plane, there is an energy minima for it to basically, there is a local minima for the sulfur atom to stay there and be stable. Having said that, of course, under the beam, we can have other types of positions for the sulfur because there is a lot of dynamics going on in these samples. Interaction of the electrons with the sulfur and other atoms. And so I basically wrapped up my talk just now. So we observed displacement in these samples, and depending on, so when we are talking about a dopant or a substitutional atom, a lot of the times we take it for granted that, Mali and tungsten are very similar. There shouldn't be any changes or strain. But the reality is that the chemistry and structure around these dopants and substitutional atoms can be much more sophisticated and can lead to asymmetry, structural distortions that are not homogeneously happening around the dopant, and that can lead to strain, that can lead to these materials to have certain applications, for example, in catalysis or other types of applications. So, there can be a lot of interesting discussions that can just happen around at the atomic scale, and the consequences of what would happen at the macro scale in these materials. by just showing this, I would like to wrap up my talk. Okay, can you go to the next slide? And tell you, beside the message we got, an understanding that we had in the transition metal glycalcogenide systems, using the TM in this talk, I tried to show you that how we can understand the atomic and chemical structure, the defects, edges, grain boundaries, dopants, understanding the nucleation mechanism in heterostructures, understanding the chemical bonds and the distortions that happen at these chemical bonds or defects at the sub-angstrom size scales and the local strain. Also, you are able to understand evolution and dynamics of these microstructures under in situ conditions, and understand their band structure. Also, by changing the condition of the microscope, we can look at these beam sensitive materials and many other applications that I did not cover. So just to wrap up, I'd like to acknowledge my group. In particular, all this work was done by my first PhD student, Amin Azizi, who is leaving this week to Berkeley to start his postdoc in the physics department. For the growth of the TMDs, I'd like to acknowledge Dr. Mauricio's Terrones group and Robinson's group. Simulations were done by Dr. Jacobson's group for tungsten disulfide at the beginning, and for the rest of the work, the simulations were done by Dr. Crespi at Penn State, and he's a student who's now going to be part of 2DCC, I believe, Dr. Yuanqi Wang. For the imaging, the tungsten disulfide work was done at National Center for Electron Microscopy at Berkeley Lab. And the rest of the work, the other two sections we used are Titan at Penn State, and I'd like to acknowledge Dr. Kevang for his help with my group. Thank you, and if you have any questions, I would be happy to answer.
Okay, so we have some questions coming in from the online group.
Okay, how do I read this? I can't read part of the question. The other one.
Okay, so we don't see any questions online right now, so we'll go ahead and go to questions in the room.
Is there any prospect to grow on hexagonal boron nitride?
We have actually done that. I haven't shown the data because I want to publish it first, and the paper is about to go out. Yes, absolutely.
Yeah, on the length of the chains, it's really puzzling that one is shorter. Is there any?
Yeah, we actually know the reason. This work we did. Actually, I have to give all the credit to Dr. Crespi's group for their patience and not giving up, because we talked a lot for a year, and we did a lot of imaging, back and forth simulations to understand why we have longer chains in one direction, and then basically this stripe formation. And what we realized was that this is absolutely not a thermodynamically driven phenomenon. This is a kinetically driven phenomenon, and it happens when you have fluctuations happening during growth. So you can have a metal terminated edge or a sulfur terminated edge, and you also can have edges where you have a higher concentration of sulfur or lower concentration of sulfur. And combining all these conditions, you have different chemical potentials for different atoms, and for each of these cases, you see in one case, moly is preferred to sit at the edge. For the other case, you have tungsten preferring. And as, for example, we are using the sulfur, let's say if we are having a, putting sulfur on the edge, we are using up the sulfur. Sulfur is gonna, there is a, a lower amount of sulfur locally at the growth edge that can lead to, depending on the edge, termination that can lead to either moly or tungsten seeking. And then again, like moly or tungsten is going to be used up, then the chemical potential for those elements are going to change. That again can change the chemical potential. It's like a a loop that feeds itself, and then you will have, by just locally fluctuating the sulfur at the edge, growth edge, you can have formation of these stripes. It's actually published in the paper is published just a few months ago, and we had a discussion on that. It was we elaborated on what the reason is for this chain formation.
Any other questions from the local audience? I see one in the back.
So for some of these materials, they're very sensitive to oxidation. So how do you get it from the growth chamber into the TEM without the sample degrading?
Okay, so we didn't have a problem. So for example, for the heterostructure growth, typically as soon as we grew the material, we had TM work happening on them within few days, and we did not have any problem with the oxidation. We have had tungsten diselenide oxidation we observed, but it happened after several days, after maybe a few months. When we put the sample back into the microscope, we saw that the edges are deteriorated, but within the time frame that we were looking at, we did not observe any oxidation problem.
Okay, we have a question online. You can see it right there on the board, Nicole.
How can this be explained? She's right. Yes, they are quite large, and they can be as large as 30 to 50 picometers. And it can be explained when you have a sulfur atom sitting on the top or the bottom. Like imagine you have an arm, you have your arm that's up or down, and then you bring it up to the horizontal plane of the tungsten. And when that happens, you're going to have the bonds expanded in one direction, and then the molybdenum atom is going to move further away. So on one side you have expansion of the bond, on the other side you have contraction. So this happens only when my lone sulfur atom is going to move to the plane of the metal. So if you go back to the slide, back right here. So you can see that this black circle is my lone sulfur atom. When it's up there, there is no changes in the bond. But when it comes down, right there, to my transition metal plane, that's where I get displacement. And unfortunately, I really apologize. We had a DFT map calculated by Crespi Group from DFT that in fact shows the same exact bond displacements, the same exact magnitude for like about 50 or so picometers. That was pretty much in good agreement with our experimental data, but unfortunately it's not showing up. But this paper is coming out, it's under review, so it's going to come out soon.
From Alina online here. Can you just repeat what she's asking online when you answer the question? Second question.
Can they be induced by electron beam, and did you try to perform TEM at low dose? Yes, absolutely, they can be induced by the electron beam, because basically electron beam, there is a lot of dynamics going on. So electron beam can provide the energy to move the sulfur into the plane. It can also provide the energy to bring it back up. We have seen other displacements with other magnitudes that that basically it's a dynamic process. It's wrong to rule out the role of the electron beam. We have tried to do low dose. Actually, in these images, we have reduced the dose slightly. We have basically defocused the probe a little bit to reduce at the gun to reduce the number of electrons here. And we did not do extremely low dose because we wanted to have an idea of where the sulfur atoms are, because when you go to very low dose, you also lose your, the quality of your images go down. With this level, at this level, we were able to get several, like 3 or 4 images without damaging the sample, because many of these images are drift corrected. So we reduced the dose in such a way that we were able to get 3 or 4 stem images with no damage before contamination started to build up on the sample. So I think we were low dose enough that we were able to do this study.
Okay, I don't see any more questions online. Are there any more significant questions here in the book model? If not, we'll wrap up. But I want to remind everyone online and everyone here that on February 23rd, we'll have our next webinar. It'll be on bulk crystal growth.